Okay, so this is lecture 30. I'm going to continue with some examples of the Poisson process. Okay, so just remember that the Poisson process, you can find the probability that x is equal to n using the Poisson distribution with parameter lambda t. And the expected value is lambda t, which is also the variance as well. Okay, so we also need a little bit of information about the holding time because we're going to be dealing with an example with the holding time. So remember, the holding time is exponentially distributed. So the state itself is has a Poisson distribution. The holding time is exponential random variable. And so here for the holding time, we have the expected value of the holding time is 1 over the rate, and then the variance is the expected value squared. Okay, so this is the problem. It's called gone fishing. So to seek a change of pace from her intense Columbia experience, Chelsea Crowder has decided to go fishing. It is conceivable that this, like everything else, could be done in a brief excursion from campus, but Chelsea wants a real change. So Chelsea has decided to go to Venice, Florida, which is centrally located on the Gulf of Mexico along the coast of southwest Florida. Not that you need to know that in order to do this problem, but a lot of word problems have extra stuff in it anyway. So, as usual, Chelsea hopes to catch some grouper and snapper, but she's also hoping to catch some other fish such as kingfish, cobia, blackfin tuna, etc., etc., etc. Okay, so we suppose Chelsea catches fish according to a Poisson process at a rate of 3 per hour. So, given that information, we're supposed to answer the following questions. Okay, so part A, what is the expected number of fish Chelsea catches in a 2-hour period? So, we know that the expected number it's being modeled by a Poisson process, and so we can think about the number of fish that she's likely expected to catch in a 2-hour period will behave according to a Poisson distribution with the expected value of lambda t. So here lambda is the rate, and that is given to us exactly, so we don't have to find it. It's given to us as 3 per hour. So we have lambda is equal to 3. So we're talking about the expected value in a 2-hour time period. So here t is 2. So we just multiply the 3 and the 2 and we get 6. So what is the variance? Remember, the variance is for a Poisson distribution is the exact same as the expected value. So again, we get 6. Okay, so what is the probability that Chelsea catches exactly 4 fish in a given 2-hour period? So again, it satisfies the Poisson distribution, because we're looking at the number of fish that she catches, not anything but time. Time would be considered the exponential distribution. So we're looking at the number. We want to know the probability that she catches exactly 4 fish in a 2-hour time period. So we have the probability that n of t is equal to little n. It satisfies a Poisson distribution. So we have the formula. We know that lambda is 3. We have our time periods 2. We want to know when our n is equal to 4, so here we have 4 for our little n, and we get 0.134. Part D, what is the probability that Chelsea catches at least 2 fish in a given 2-hour period? So we're not talking about exact now, we're talking about at least 2 fish. So we're looking at the probability that the number of fish she catches in a 2-hour time period, so n of 2, is greater than or equal to 2. We can think about this as the probability as 1 minus the probability that she catches less than 2, because we know something about how to find, we know the probability of n equal a number. So we want to somehow relate this to the probability of n equal a number. So here we can first think about this as 1 minus the probability of n of 2 is less than 2. So what does this include? This includes if she catches 0 fish or if she catches 1 fish. So the probability that n of 2 is less than 2, we have to think about adding together the probability that she catches none plus the probability that she only catches 1. Both of these we can use our formula. So here we have little n is equal to 0, little n is equal to 1. Both cases we have the rate is 3 and the time period is 2. So finding this, we get a 0.8785. So there's a pretty good possibility that she's going to catch at least 2 fish in a 2-hour period. So this is a really good probability. Okay, so now let's see, part E. what is the conditional probability that Chelsea catches exactly 4 fish, so we're talking about exact now, in a given 2-hour period, given that she catches 23 fish in the previous 2 hours. So you might think that catching 23 fish in the previous 2 hours, there's not a whole lot of fish left. And you would think that there definitely wouldn't be a lot of fish in order to catch 4 more fish. Or you could think opposite. You could think, okay, so she's caught 23 fish, so the fish are really biting, so maybe there's a good possibility that in the next 2 hours she's going to catch 4 fish. You can think of it different ways. So for our purposes, we're considering this as a Poisson process. So what we're looking for is we're looking for the probability that in the next 2 hours, given whatever hour we're at, whatever time we're at, we're looking at the possibility that in the next 2 hours at t plus 2, that this is equal to 4. Given the fact that in the previous 2 hours, so this is the previous 2 hours, so here's our time and this was our 2 hours before, we caught 23 fish. So now you have to remember that we're talking about a Poisson process. So according to this model, the conditional statement makes no difference because the Poisson process has stationary and independent increments. So what happens in one time period has no effect in what happens on the next time period. So in other words, basically what we can say is this probability that we're looking for is simply the probability that n of t plus 2 minus n of t is equal to 4. So we just have this probability. And remember, we can say the distribution in any 2-hour time period is the same, so we can think about this as just n of 2 equals 4. What's the probability that n of 2 is equal to 4? Using, again, our formula, we have this probability is 0.134. So this is the same answer that we got in part C. Okay, so part F, what is the conditional expected number of fish that Chelsea catches in a given 2-hour period, given that she catches 23 fish in the previous 2 hours? So this sounds a lot like what we did before. So here we're looking for the expected number. And we're looking for the expected number given that she caught 23 fish in the previous 2 hours. But again, just like in the previous part, we have independence. So the expected value, so here what we're looking for is we're thinking about what's the expected value for the next 2-hour time period, given that in the previous 2-hour time period she got 23 fish. So that's how you write this. This is simply the expected value of n of t plus 2 minus n of t, because the given part doesn't make any difference because, again, it's independence. Doesn't matter what time period we're looking at because the distribution is the same. So technically the time period makes a difference, but the distribution is the exact same, which is why we can write this e of n plus 2 minus n of t is the same thing as just n of 2. So a 2-hour time period, which is the exact same thing that we got in part A. Okay, so now this one's a little bit different. What is the expected time until Chelsea catches her 4th fish? So we're looking at what is the expected time that she's going to catch her 4th fish. Okay, so for the Poisson process, in any continuous time Markov chain, so here we're looking at expected time. So remember the time is given according to an exponential distribution. So remember what it means for the exponential distribution. The mean length of the interval between successive catches is 1 over lambda. So this is the mean of our exponential distribution. So remember what I summarized in the previous lecture and at the beginning of this lecture. So for an exponential distribution, the mean length of the time interval between successive catches is going to be 1 over lambda, 1 over the rate. So here the mean length of time between catches is 1 over 3, because our rate is 3, which is 20 minutes. So this is the length of time for one catch. So let Ti be, and that should be B, not bet, be the length of time interval between catching her I minus first fish and her ith fish. Then what we want is the expected value of T1 plus T2 plus T3 plus T4. But these are all independent, so the expected value for each fish is the exact same, so we can just say that's 4 times the expected value of just catching the first fish. So this is going to be 4 times our 1/3, which is 4/3 hour or 80 minutes. Okay, so now let's talk about different fish. So suppose in addition that each fish Chelsea catches is a grouper with a probability of 1/4, a snapper with probability of 1/3, and some other fish with a probability of 5/12. So here we're thinking that there are so many fish that could be caught. So the likelihood that you're going to catch a grouper, however many fish Chelsea catches, the likelihood that she's going to catch a grouper is 1/4. The likelihood she's going to catch a snapper is 1/3. The likelihood that she's going to get something else is 5/12. So what we want to know is what is the probability that Chelsea catches exactly 8 fish in a given 2-hour period. And not just exactly 8 fish, but we want 3 of them being grouper and 5 being a snapper. So now we need to think about this a little bit differently. So here we're going to let NG be the number of grouper, because we've got to separate them. NS is the number of snapper, and NO is the number of other fish caught in the time interval from 0 to T. Okay, so each of these, NG, NS, and NO, are all independent stochastic processes, and they're independent Poisson processes. So the rate of an individual Poisson process is going to be the overall rate, which is R3, times the probability of catching that type of fish. So we have a rate of 3, and then we have the probability of catching a certain type of fish. So here, in G of T, remember the probability of catching a grouper was 1/4, so our rate for our Poisson process in G is 3 times 1/4, or 3/4. We had a probability of 1/3 of catching a snapper, so our rate for our Poisson process is 1, and we have the rate for catching other fish is will be 15 or 12 or 5/4. So then what we're looking for is we're looking for the probability that we catch 3 grouper, 5 I think these were snappers, and none of the other kind of fish. Okay, so here we have a 2-hour time interval. We have different rates now. So here our rate for the grouper is 0.75. So here we have the 0.75. Here we have the rate for the snapper, and here we have the rate for the other fish. We have the number of fish, the 3 here for the grouper, the 5 for the snapper, and the 0 for the other fish. So we multiply all these together and we get our probability that this is. So it's not very likely that she's going to catch exactly 8 fish of this kind in a 2-hour time interval. Okay, let's see. And that was the end of these problems. So the next homework assignment, part of the next homework assignment is going through this gone fishing and doing some other examples that are similar to this on the assignment. Some are using an exponential distribution, some require you to use the Poisson distribution. And so you have to really just read the question and figure out whether it's talking about time or the number, the Poisson process, or the holding time. So you just got to figure out really what it's talking about. And then the next time, in the next week, we're going to go back to just general continuous time Markov chains and talk about those.